So I wanted to take this opportunity to talk about some ancient things that have been forgotten by most people, particularly the authors, me and some others. Though every now and then I get papers that have a title on a conjecture of Nathanson. And I have no idea what the conjecture is, and I look up the paper, and there was such a paper, but I can't understand it anymore. But I thought it's worth sometimes dredging these things up because they're so interesting. So there are 4 talks. Each of the 4 talks are more or less independent of each other. And I also want to give in each talk a different method. So there are 4 different methods in the talks. So today's talk is clearly the polynomial method. Tomorrow's talk, and maybe a bit of Wednesday's, is on a combinatorial method. There will also be what I would call the anti-probability method. The anti-probability method is the following. When I used to work with Erdos thought in probabilistic terms. And I have no emotional connection to probability. So I would try, whenever possible, to take the probability argument and turn it into a counting argument, a pigeonhole argument. And so, but if you understand probability, when I get to that part, you'll see why the probability, where the probability must have been. And then the 4th talk will use Ramsey's theorem to prove some results in additive number theory. Okay, so I'm actually not used to these computer things. So I also have actually no idea how long this talk will take because I just wrote up all these slides, but we'll see. So let's start. The other thing is, the 1 or 2 times I've given a computer talk, I always feel like I'm at someone else's talk. And these slides go up, and I say, oh, yeah, that's interesting. Yeah. So let's just recall. We start with an additive abelian group or a semigroup, like the integers or the non-negative integers, or the congruence classes modulo or prime. And what we're interested in is adding things up. So if you take 2 subsets A and B, the sum set is just everything you can write as an element of A and an element of B. And sometimes you want to restrict yourselves to distinct sum ends. So the restricted sum set, which is this A plus with little wedge sign on top, means everything of the form A plus B, where A and B are different elements. And more generally, if you take H different subsets of a group, you look at the sum set A1 up to AH, which is everything in every element of the group that can be written as a sum of an element of A1 and an element of A2 and so forth, up to an element of A sub H. And in particular, if you just take one set A and you add it to itself H times, we have what's called the H-fold sum set. And if you require this sum ends to be distinct, it's the restricted H-fold sum set. So there's simple questions to ask. If you have 2 sets A and B, what is the sum set? Like, what numbers are sums of 2 squares or 2 cubes or a square and a cube? If you have a set C, is it the sum of 2 sets, A and B? Or if you have a set C, at least are there sort of large sets A and B where the sum set is contained in C, or maybe the symmetric difference between the sum set and C is small? If you have a set C and a set A, can you somehow find a large set B where A plus B is contained in C? If you have 2 sets A and B, can you find in some way lower and upper bounds for the size of the sum set? Or if you take an element in the sum set, maybe you have different ways to write it, different representations. And what can you say about the representation function? So in all of these are all very simple questions, and in all of these questions there are a small number of results and a large number of things which no one has any idea how to deal with, but there's natural questions, there's simple questions. So what about size? So if you take a set of integers, what is called the counting function just counts the number of positive elements in the set. You don't count 0. And what is called the Schnirelmann density of the set, you take the counting function a of n over n and you take the inf, not the lim inf, but the inf. It's a rather curious notion of density, but it was, what I think was really the first paper in additive number theory in the 20th century was a paper by Schnirelmann, where he introduced this curious notion of density, and he proved a certain inequality about the density of the sum of two sets. This is Schnirelmann's inequality. Schnirelmann also was evidently the first person who could understand Brunn's paper on the Brunn sieve, and putting these things together, he got the first non-trivial result on the Goldbach conjecture. So this inequality of Schnirelmann for the density, the Schnirelmann density of the sum of two sets, I mean, of course, the density can't be bigger than 1, but a lower bound is the density of A plus the density of B minus the product of the densities. For a long time, it was, people would have preferred if this sigma of A, sigma B term wasn't there. And it was an open question, in fact, whether the stronger inequality would hold without this sigma of A, sigma of B. At one time, this was a very fashionable open problem, and it was finally solved by Henry Mann, who proved this inequality for the Schnirelmann density of sumsets, which is best possible and very beautiful. He uses what is sometimes called the Dyson E-transform in this paper. A little bit shortly after Mann published his paper, Emil Artin and Peter Shirk published what seems to me essentially the same proof with the same transform. And Freeman Dyson, probably when he was still an undergraduate at Cambridge, generalized this result to more summands. And I guess it's from Dyson's paper that maybe more people read Dyson's paper. And so this transform that occurs is often known as the Dyson E-transform. The lower asymptotic density is a more natural. You take the lim inf of this A of n over n. And if the limit actually exists, I didn't write this down, but if the limit exists, then we just call it the asymptotic density of the set A, and we drop the subscript L. So that's the lower asymptotic density of a set of integers. And there is a truly beautiful theorem unknown to practically the entire mathematical world about the asymptotic density of sumsets. So if you have a set of integers A, and you take a positive integer G, you just look at all of the congruence classes, mod G, that have a representative in A. So you simply take the set A and just fill it out. So you just add, if an element is an A, you put in the whole congruence class of A mod G. So that's what this A superscript G means. And also, this A squiggle B just means that two sets of integers coincide from some point on. So Knaser, Martin Knaser, I think it was his doctoral thesis in Germany in the 1950s, proved a theorem about a lower bound for the asymptotic density of sumsets. And I'm just going to give a special case. So this is a special case of Knaser's theorem. There's what's essentially a special case of this, which is the version everyone talks about subsets in sumsets in a finite abelian group. And you can almost get it from this theorem. But Knaser's theorem on asymptotic density says that either the right inequality holds, the one that you really hope would be the case, which is that if you take a set A and add it to itself h times, the density of the sumset is at least h times the density of the set. But of course, sometimes that doesn't happen. If you take the even integers, it has density 1/2. If you add the even integers to the even integers, you get the even integers, which has density 1/2. But 2 times the half is 1. And so it's not true that a half is greater than or equal to 1. So the inequality you hope would happen doesn't always happen. But what Knaser showed, that this sort of simple counterexample to the inequality is the only counterexample. So Knaser's theorem says that if this inequality that you would like doesn't hold, then there's a positive integer G such that A, if you take A and you just look at all the congruence classes mod A, the sumset HA is the same as the sumset of the congruence classes. And the density of the sum, and of course, if this is true, if you take a set of congruence classes that has an asymptotic density, congruence classes mod G, If you have R congruence classes, it will have density R over G. So the lower asymptotic density is actually an asymptotic density. And the density of HA is greater than or equal to H times the density of A minus this quantity. So in the example I gave, where you take the even integers, you're just adding them to themselves, H is 2, G is 1, and you get a statement which is true, which is a half is greater than or equal to 1 minus a half. So there is some justice in this mathematical world. This is Kneser's theorem. It is a fantastic theorem. You have to read German to appreciate it, however, because you have to go back and read his paper. It's also in this great book of Halberstam and Roth called Sequences, but I always found their exposition incomprehensible compared to the way Kneser wrote the paper. So it's worth learning German just to read this paper. And we're going to use this theorem tomorrow. What about for finite sets? So here we've been talking about the sum of infinite sets of integers. Suppose you take a set X, a set of integers, take a set A of integers, a finite set of K integers. So we have two simple inequalities that if you have K integers in A, the sum set has at least 2K minus 1 elements. And if you look at the restricted sum set, it has at least 2K minus 3 elements. And the proof of the first is one line. Namely, if you have K integers, you have A plus A, A1 plus A1, A1 plus A2, and so forth, up to A1 plus AK, and then A2 plus AK up to AK plus AK. So you have this strictly increasing sequence of 2K minus 1 integers contained in the sum set. So every sum set contains at least 2K minus 1 numbers. And if you want to look at the restricted sum set, where you don't allow an element to be added to itself, you do the same thing, only you just start with A1 plus A2, A1 plus A3, A1 plus AK. They're strictly increasing. A2 plus AK up to AK minus 1 plus AK, and there are 2K minus 3 numbers there. So we have those, simple inequalities, but there's a theory, of course, that everything in mathematics is simple. And if you think it's not simple, that just means you haven't understood it yet, and you have to keep working at it. Congruence classes. So we can ask the same question about sets of congruence classes. So let's just take congruence as modulo of prime P, K congruence classes. And we have, in fact, exactly the same inequalities with the obvious condition that there are at most P congruence classes mod P. So if you add a set of K congruence classes to itself, you get at least 2K minus 1 congruence classes, and unless 2K minus 1 is bigger than P, in which case you get everything. And the analogous statement holds if you take the restricted sum. Now, the first inequality has been, it's even on the poster for the conference, I think, is called the Cauchy-Davenport theorem. And the second inequality is the Silva-Hamidoune theorem. It used to be called the Erdos-Turan conjecture, and then it was proved by Silva and Hamidoune, so that's the theorem. And so that's what I'm going to prove. There are Aleph naught proofs of Cauchy-Davenport, and but there were not Aleph naught proofs of the Erdos-Turan conjecture. There was none. And then Silva and Hamidoune gave a proof, and shortly thereafter, there was a different proof, not necessarily simpler, but a different proof using elementary facts about polynomials. And it's hard to understand. It's hard for me to understand why things become popular in mathematics, but just because the polynomial method to prove the Erdos-Hamidoune theorem was so pretty, a lot of people paid attention to it. And over the last 25 years, it has been used in various forms to prove many more results. And even though, so to give a flavor, so I'm going to prove, this is the only thing in my talks I'm actually going to prove in detail. And I'm going to start by using this polynomial method to prove the Cauchy-Davenport theorem. So there's only one fact from algebra you need to know, which they teach in high school, which is that polynomial in one variable with coefficients in a field of degree k has at most k roots. Right? That is the polynomial method. Okay. So we're going to start with this. This is how you use some simple facts about polynomials to prove Cauchy-Davenport and then to prove Erdos-Turan. So there are a couple of little lemmas that we need. We're in a field like Z mod PZ. Take k elements in the field, a set A of cardinality k. And for every integer m, there's a polynomial of degree at most k minus 1, g sub m of x, where g sub m of a to the I is a to the I to the mth power. All right? And why is that? So here's this polynomial g sub m. And what we want is that g sub m of ai, it's just u naught plus u1 ai, u2 ai squared, so is ai to the m. So if you look at that as a system of linear equations where the coefficients are these a's, you have k linear equations in k variables. The k variables are the coefficients of the polynomial. And for example, the determinant of that system of equations is the non-zero Vandermonde determinant. So you can solve the linear equations and you get the existence of these polynomials. I mean, you can do it by Lagrange interpolation. You can do it in whatever is your favorite way to construct a polynomial. But these are important polynomials in this application of the polynomial method. Another lemma. So these two lemmas are very important. So this lemma says the following. If you have a polynomial in h variables, which for whatever reason I'm denoting x naught, x1 up to x sub h minus 1, and I'm not interested in the total degree of the polynomial. I'm interested in the degree of the highest degree that each variable occurs in the polynomial. So in this polynomial, the variable xi has degree at most k sub I minus 1. And suppose you take non-empty subsets of the field, a naught up to a sub h minus 1, and the number of elements in the set ai is ki. So if this polynomial vanishes, so if of a naught, a1 up to a sub h, if that's equal to 0 for all of these h tuples, then the polynomial has to be the zero polynomial. And in one variable, it just says that a polynomial degree k has at most k roots. And then you use induction on h. Right? Now, Noga Alon has, a few years later, he wrote a kind of a survey paper, which he calls something like the combinatorial Noshtalanzatz. But this is it, right? So this is what we use. So this lemma, in the special case of two variables, which is all I'm going to use, says the following. If f of xy is a polynomial with coefficients in this field f, and of degree at most k minus 1 in x and l minus 1 in y, and you take subsets of the field, a is k elements and b is l elements, if f of a b is 0 for all a b in this product, then you have the zero polynomial. Okay, and again, some simple counting lemmas. If you take any finite set A, take two subsets A and B, A intersect B is at least the size of A plus the size of B minus the size of the whole set, and that just comes from this basic Boolean inequality. Yeah. Lots of little things. Everything is little. Right? A few pennies adds up. In a group, we also just need to define the difference set. So if you have two subsets A and B, if you look at all the elements of the form A minus B, where A is in the set A and B is in the set B, that's called the difference set, and X minus A is just a special case of the difference set. and one lemma, maybe one more, maybe this is the last guy. If you have two subsets of a finite abelian group, A and B, and the size of A plus the size of B is strictly bigger than the size of G, then the sum set is the whole thing. And again, every proof is one line. If you take any element in the group, if you look at the difference set, C minus A intersected with B, by this previous inequality, that's at least the size of this plus the size of this minus the size of G. But a translate of a set has the same size as the set, and this difference is at least 1. So there's something in this intersection. So there's an A and A and a B and B, where C minus A equals B, so C equals A plus B. So every element is in the sum set. It's nice. Okay, so here's the proof of Cauchy-Davenport. Now, take two sets A and B and the integers mod P. K elements in A, L elements in B. Now, if K plus L was P plus 1 or greater, the sum set would be the whole group by this previous lemma. So we only have to consider the case that K plus L is less than or equal to P. And we want to prove the inequality that, the size of A plus B is at least K plus L minus 1. So the proof is by contradiction. That's called C, the sum set. And suppose the sum set is has at most K plus L minus 2 elements. So R, which is K plus L minus 2 minus the size of C, is some non-negative integer. And because this is called the polynomial method, I need a polynomial. So here it is. So I take x plus y to the r is this thing, times this product, x plus y minus c, for every element in the sum set. So the degree of this product is the cardinality of C. The degree of this is R, and the cardinality of C plus R is K plus L minus 2. So this is a polynomial of degree K plus L minus 2. There's my polynomial. And if I take an element of A and an element of B and I plug it into the polynomial, A plus B is in the sum set. So A plus B is equal to one of these C's. So for all A, B in this product, f of x, y, f of A, B is 0. Right? Now, of course, I can't use my lemma, this sort of Null-Stellensatz type lemma, because the degree of x in f is not at most k minus 1, and the degree of y in f is not at most L minus 1. So I need to take care of that annoying little thing. And so I have these polynomials that I constructed a few minutes ago. For every m, I have a polynomial g sub m of x of degree at most k minus 1, where g sub m of a is a to the m for every a in the set capital A. And similarly, I have polynomials h sub n of y for every n of degree at most L minus 1, where h sub n of b is at most b to the n. Right? So what do I do? So here's this polynomial. So if you expand it, it's x plus y to the k plus L minus 2 plus lower order terms. So one of these terms, I suggest you use the binomial theorem. So one of these terms is k plus L minus 2, choose k minus 1, x to the k minus 1, y to the L minus 1. And then I have all the other terms from the binomial expansion, and plus the lower order terms. Now, here I have an x to the m, y to the n monomial. If m is k or greater, I can replace x to the m with the polynomial g sub m of x, which is a polynomial in x of degree at most k minus 1. So this will have degree at most k minus 1 plus L minus 2. It'll be k plus L minus 3. This will have degree lower than k minus 1, x to the k minus 1, y to the L minus 1. And similarly, if n is greater than or equal to L, I can replace y to the n with the polynomial h sub n of y. And I end up with some expression in monomials where, again, the degree of x is at most k minus 1. The degree of y is at most L minus 1. And the only term with degree of x k minus 1 and the degree of y L minus 1 is this first term. And this coefficient mod p is non-zero, because k plus L is at most p. That's what I just said. So when I make this substitution, I get some new polynomial, the same leading term, plus these other terms where m and n are at most k minus 1 and L minus 1 respectively, and the sum is at most k plus L minus 3. So this polynomial has degree k minus 1 in x, L minus 1 in y, and f star of AB is 0 for all AB in this product. That's a contradiction. All right? So we have our inequality. That's the Cauchy-Davenport theorem. Now, to deal with the Erdos-Turan conjecture, that is to give a polynomial proof of the Diaz de Silva-Hamidoune result, we have to be an epsilon sneakier, but really a small epsilon. It's not that. So again, we have a couple of very elementary lemmas. Suppose you take a finite abelian group that has no two torsion. That just means that if x is in the group and x plus x is 0, then x is 0. So in this case, if the size of A plus the size of B is at least cardinality of G plus 2, then the sums of pairwise distinct elements A plus B gives you the whole group. In the previous case where we didn't look at distinct summands, we had a 1 here instead of a 2. So, but the proof is essentially the same. Take any C in the group, and this intersection is at least the size of this plus the size of this minus the size of the group. This is a translate, so the cardinality of C minus A is the cardinality of A. And this difference by the inequality is at least 2, which means you can find two elements, A1 and A2 in A, and B1 and B2 in B, such that A1 plus B1 and A2 plus B2 equals C. Now, if you were so unfortunate that A1 equaled B1, that these were not distinct summands, and these also were not distinct summands, then you would have 2A1 plus 2A2 equals C, or 2 is, subtract. 2 times A1 minus A2 is 0, but because there's no two torsion, this element is 0, and A1 equals A2, which is absurd, so we can represent C as a sum of distinct elements of the group. Okay. So this is the theorem we're going to prove. It's a tiny, tiny, tiny bit stronger than the Erdos-Turan conjecture, but that's okay. And then, so this says that if you take finite subsets of the group of the congruence classes mod P, K elements in A, L elements in B, and we have this curious condition that A and B cannot be of the same size. So K, let's say, is less than L. And K plus L is less than or equal to P plus 1, then we have this inequality. Again, by the little lemma we just proved, if K plus L were at least P plus 2, then this would be the whole group. So the only interesting case is when K plus L is the most P plus 1, and we want to prove this inequality. So suppose it's not true. So the set of distinct sums, A plus B hat, has at most K plus L minus 3 elements, and R is K plus L minus 3 minus the size of C. We need a polynomial of degree K plus L minus 2, which is of degree at most K minus 1 in X and at most L minus 1 in Y. So here's a polynomial that satisfies the first but not the second of those conditions. The degree, the total degree is K plus L minus 2. We look at X plus Y to the R, the product for every C in this set of distinct sums, X plus Y minus C, and then this additional factor, X minus Y. Now, this polynomial does satisfy the condition that for every pair AB, f of AB is 0. And the reason, of course, is that if A is different from B, then A plus B is a sum of distinct elements, so it's an element of C. This gives you 0. And if A equaled B, this would give you 0. So, but we got to get the degrees of x and y down to where we would like them. And of course, you don't have to think very hard. I mean, if a trick worked once, then maybe it works twice. So we do the same thing that we did for the Cauchy-Davenport theorem. For every m in n naught, for every non-negative integer, you take your polynomial g sub m of x of degree in x of at most k minus 1, and g sub m of a is a to the power m. And for every n, you have a polynomial in y, h sub n of y, of degree at most L minus 1, with h sub n of b equal b to the n. And you plug them in wherever you have to. So this is my polynomial, x minus y, x plus y to the r, so forth. So this is really x minus y times x plus y to the k plus L minus 3. That's the total degree of this part, and then lower order terms. And you distribute, right? It's x times this minus y times that. And you actually get two terms with the monomial x to the k minus 1, y to the L minus 1. Here, when you take the binomial coefficient k plus L minus 3, choose k minus 2. And here, when you take the binomial coefficient k plus L minus 3, choose k minus 1. And then you have lots of other terms. X to the m, y to the n. The only condition is that mn is not k minus 1 comma L minus 1. And the important note is, if you look at the difference of these two binomial coefficients, it's this. And here's the only point where we needed the fact that a and b had different sizes, that k was different from L. So this binomial coefficient is not 0 mod p. Right? So we do the replacement that we did before. When you have a monomial x to the m, y to the n, where m is at least k, you replace it with g sub m of x. When you have a monomial x to the m, y to the n, where n is big, greater than or equal to L, you replace y to the n with h to the n of y. Again, this is a polynomial in x of degree at most k minus 1. This is a polynomial in y of degree at most L minus 1. So you get some non-zero polynomial, because here every monomial has total degree at most k plus L minus 3. This is degree k plus L minus 2. This has a non-zero coefficient. So this is a non-zero polynomial. Degree k minus 1 in x, degree L minus 1 in y. And if you plug in AB, you get 0. And that's a contradiction. So we prove this inequality. Okay? And to get the Erdos-Turan conjecture and the theorem of Diaz de Silva and Hamidoune, they were adding a set to itself. We need to have two sets of different sizes. So, you do the stupidest thing possible. You have a set A, call your first set A. Take an element of A, throw it away. You have a slightly different set B, has one element less. That's your set B. And so instead of a 2 here, because it would have been k plus L minus 2, but I'm letting A be the original set, B be the set with one fewer element. So L is k minus 1, and this is 2k minus 3. That's what it is. Okay. So that's the Erdos-Turan conjecture. There's nothing to the polynomial method that you cannot teach. I was going to say to a really smart high school kid, but you have to be a little bit familiar. I mean, it doesn't use very much in the way of machinery. Now, let me make a couple of sort of bibliographical notes. So these are the two papers that of Lon Ruja and myself from 25 years ago. And of course, what the Erdos-Hamidoune, the Erdos-Hamidoune conjecture and the result of Diaz de Silva and Hamidoune applied not just to the case when you're adding a set A set to itself, not just two-fold sums, but also to h-fold sums. That's a little bit more complicated. And a proof of that is, well, it's in our paper in the monthly, we just did the case h equal 2. In the paper in the Journal of Number Theory, we did the general case. And the general case is also sort of exposed in this book. Because this polynomial proof is so elementary, no one looks at this Diaz de Silva and Hamidoune paper. What they use is a little bit more algebra. You have to know some linear algebra, some exterior algebra, and a little bit about the representations of the representation theory for this metric group. It's a beautiful, beautiful paper. Hard to read, perhaps, but I gave, there's an exposition in my book of the Diaz de Silva and Hamidoune proof also, where I could take out the representation theory, because there was a little bit, they sort of like knew too much when they were writing the papers, and you need a little bit less algebra, but the crux of it is really in the linear algebra and the exterior product stuff. Now, there seems to be a belief that this polynomial method really originated in number theory in these two papers, and in graph theory in an earlier paper, a couple years earlier, by Noga Alon and Tarsi. But of course, people have been using polynomials to prove things in number theory and everywhere else for 100 years or more. And there's a very nice survey paper by Terry Tao that was in the European Math Society surveys on this polynomial method. And he's very careful. I mean, he just gives this beautiful survey of stuff going back well into the 19th century, using essentially the same kinds of ideas. I mean, there's nothing, who will understand this? Ein hatash mitachat hashemesh. You understand that? Oh, so this is from Ecclesiastes. There's nothing new under the sun. So people seem to think at the time that this method was new. But it's, nothing easy is usually so new. Okay, so, all right. All right. So let's just say end of part 1, now start of part 2, okay? Because I wanted to start, I mean, I noticed when this series of talks was advertised as the polynomial method, so I had to start by giving the polynomial method. The only thing is, I have reached the limit of my technological capacity. So on this computer, there are 2 files of mine. One is this, and then there's another file, which is like the next set of slides. This is supposed to say part 2 and not lecture 2, but so this is more additive number theory. So the polynomial method went back 25 years. This goes back 50 years, right? To when I was a graduate student, actually. So, so we have sets of integers. We look at the h-fold sum of the sets of integers. And if you have a set of non-negative integers, and every number, or every sufficiently large number, is a sum of h terms from the set, then it's called an asymptotic basis. So the largest part of additive number theory is the study of special cases. Sums of squares, sums of cubes, Waring's problems, sums of primes, sums of polygonal numbers. So we're interested in this general notion of when is it the case that you have a set of integers and every number from some point on is a sum of h, not necessarily distinct terms from the set. And a key, still, this is a conjecture, it's still a theorem, not a theorem. A key problem is in a paper of Erdos-Turan from, I've already forgotten, about 1941, I think, which says the following. So there's something we can call the representation function. So RAH of n. So you set A of integers, h is a fixed positive integer, and this counts the number of ways you can write n as a sum of h elements of A. And you can define different representation functions depending on whether or not you care about the order. I mean, it's not an essential difference. So this is now simply just the set of H tuples of elements of A, which sum to n. So these are all, so you're counting the number of representations of n. And to say you have an asymptotic basis of order H means this representation function is positive from some point on. And the Erdos-Turan conjecture says that if the set of integers is an asymptotic basis, then its representation function is unbounded. That is, if every number from some point on has at least one representation, then there are numbers with arbitrarily large representations. So some of us were in a car yesterday talking about how you do research in mathematics or what you should do. And Shalom said, well, you should find a problem you're interested in. So this was a problem I was interested in and still interested in. And in fact, the whole body of work that I'm going to talk about for the next 3 days is really based on this conjecture. Right? That is. So let me, yeah. So if you, and it's a simple conjecture. It was actually, if you looked at the original Erdos-Turan paper, it's almost as an afterthought. It's a very short paper about something else. And at the very end, they say, in effect, by the way, is this true? And so even in the case h equal 2, this is unsolved. So again, let's recall the counting function of a set of integers. It just counts the number of elements, positive elements in the set up to x. And if you have any asymptotic basis of order h, the counting function has to be at least n to the 1 over h. That is, a of n is at least some constant times n, the hth root of n for n sufficiently large. And the proof is one line. Namely, you have a of n. We're not counting 0 in a of n, but 0 might be an element of the set. So the number of non-negative integers in this set up to n is a of n plus 1. A of n plus 1 to the h is the number of h tuples. If you get every number greater than or equal to n, the number of h tuples has to be at least this, and that gives the inequality. So that's the sort of like the lower bound for the rate of growth of any possible asymptotic basis of order h. And we say that the basis is thin if the lower bound is also an upper bound, if a of n is the most n to the 1 over h. And these things exist. They were proved, the existence was proved long ago by Raykov in the former Soviet Union in maybe the 1940s, and Alfred Sturr in Germany. You can construct asymptotic bases of order h that are thin. And there's a beautiful theorem of Cauchy's that says you can actually make this very precise. It's a somewhat complicated construction, but you can actually construct a basis for the non-negative integers of order h, where the term a sub k, the kth term in the sequence, is some constant c times k to the h plus big O of k to the h minus 1. Now, there's another notion of sort of smallness for asymptotic bases, and it's the following. We say that an asymptotic basis is minimal if no subset's an asymptotic basis. So this is a little bit subtle in the sense that you have your asymptotic basis. That just means every number with a finite number of exceptions can be represented as a sum of h terms. So what does it mean to be able to be minimal? It means if you throw away a set, it's no longer an asymptotic basis. That means every element, if you remove it, somehow destroys the representations of infinitely many numbers. So it's not so obvious that such a thing exists. And if you can make that slightly more quantitative. So for an element A in this set, this is the h-fold sumset of A. This is the h-fold sumset of A with the element little a removed. So these are the number of things that are destroyed. This is the set of integers no longer represented if you delete the element of A. And to say you have a minimal asymptotic basis means that this set is infinite for all A. And sometimes you can impose actually a stronger condition, or you observe a stronger phenomenon, that this exceptional set, the number of elements that are destroyed by the removal of A is actually quite large, is large in this sense. So 50 years ago, this was the idea. I wanted to prove the Erdos-Turan conjecture. There are two possibilities. It's true and it's false. So everyone tried to prove it was true. So if it were going to be false, what would be a possible counterexample? So you might try to find an asymptotic basis A that is somehow, see, you want a basis which has uniformly few representations. So for example, if you have a basis, and if you can throw away some elements, and you still have a basis, that only reduces the number of representations. So try to get a minimal thing to start. Or maybe you want something small in terms of the distribution of elements, the rate of growth, a thin basis. So the idea was that maybe a counterexample would be an asymptotic basis that is both thin and minimal. Do those bases exist? Because it also was from the following point of view, that even if you could look at the bases with these two properties, that might tell you something about the Erdos-Turan. It might give you a way to prove the Erdos-Turan conjecture if it were true. So these guys do exist. It is possible to construct minimal asymptotic bases that are, well, yes, they exist. Even strongly minimal ones exist. And the first example of this, exactly 50 years ago, says that if you take the set of all finite sums of distinct even powers of 2 and the set of all finite sums of distinct odd powers of 2, and you take the union of them, you get a set which is both thin and a minimal asymptotic basis of order 2. Unfortunately, this set and every example of such sets that have been constructed have unbounded representation functions. The representation function tends to be very small most of the time, but then it has peaks. And there is still nothing close to a classification theory or a structural theory, either for thin bases or for minimal bases, for any of these extremal structures in additive number theory. It's like botanists exploring the rainforest. Years ago, I knew a guy, he was a botany graduate student at Harvard, and he spent 9 months of the year in his laboratory, doing whatever you do, studying photosynthesis or whatever. But then every summer for 3 months, he went into the rainforest in Brazil, collecting species and bringing them back to the Harvard Botanical Gardens Library. So it's sort of like this with these exotic structures in additive number theory. And I think tomorrow what I'm going to do is talk a little bit more about these extremal sets, minimal bases. On Wednesday, a dual notion, which is called a maximal non-basis. And then some theorems about oscillations between them. And then on Thursday, the multiplicative analog. There's a multiplicative analog of the Erdos-Turan conjecture. The Erdos-Turan conjecture says that for additive bases, if you have a set of integers and every number from some point on is a sum of 2 terms in the sequence, the representation function is unbounded. The multiplicative version would say, if you have a set of positive integers, and if every number from some point on is a product of 2 numbers in the set, then the multiplicative representation function should be unbounded. Now, if you had to flip a coin and guess which is harder and which is easier, I know no way. I would flip a coin, right? I don't know how you tell whether one is easier or one is harder, except the multiplicative version is known to be true. So Erdos proved the multiplicative version quite a long time ago. Nesitro and Rodel gave a very beautiful proof of the multiplicative version using Ramsey's theorem. And you can use Ramsey's theorem to give a much more general statement about multiplicative systems. So that's, I guess, the last thing in this series of talks. And with that, I thank you very much for your attention.